All right, the live stream has begun. Wave to the future audience. Wave to the future audience.
Time travel. Did you post it? No, yeah.
I'm ready to post. Geoffrey, are we all good?
I'm ready.
All right. The link is on the Discord. We'll give it a few minutes for everyone to pop in.
So how's the conference been today?
Yeah, it's been pretty busy. Yeah, like we've got workshops.
Yeah, we've had like back-to-back workshops.
Yeah, starting from 9.
Like 9 a.m.
Are your eyes still feeling like happy? You have happy eyes, or your eyes wanting your eyelids to close?
Yeah, but caffeine is saving us. So
yeah. Jerry has consumed a lot of caffeine.
Yesterday, not too much today. But yeah, people should start trickling in. We should wait like probably till like give it like 3 to 4 minutes, and then yeah.
Yep. This is one of the talks where there will be sort of more activity on YouTube, just because there are a lot of interested participants that are unable to make the time because they're in a European or EST time zone.
Okay. European.
Yep, we have a couple European, or I say a couple. A good
percentage.
It's like 8 hours, so it's like 4 a.m. there, or
yeah. So unfortunately, the European ones won't be able to join us.
Okay. Tony, I'll make you host.
Yep.
Okay.
All right. We'll give it another few minutes for everyone to pop in here, and then we will head right into it. All right. Why don't we go into it here? So Geoffrey is a PhD student in computer science at the University of British Columbia and has a background in molecular biophysics and structural biology. And in this session, Geoffrey is going to give us an overview of AI and ML for science, its recent history, applications for the common good, tools, and educational advice. So thank you so much, Geoffrey, for doing our talk for the event today. And the floor is all yours.
Thank you. Thanks very much for inviting me and for all your hard work organizing. Because we have a smaller audience in the just starting out here, anyone who wants to post in the chat or say out loud, just unmute. What is your background, your academic background, especially scientific background, if you have any? And what are you most interested in this space? So maybe Sahil wants to lead us off, if you're brave enough. Okay, computer science undergrad. Yes, good.
Yeah, as for me, oh, can you hear me?
Yes, Charles, we can hear you.
Oh. Okay, yeah, so as for me, it's biomedical engineering.
Great.
And computer science as well on the side.
That's a great combination. Very good.
Yeah.
And what are you most interested in this area?
Yes. First of all, I think the there are many aspects. There's hardware, there's software, and the fact that there are models that one can develop, and then use these models to be able to predict diseases, use these models to be able to predict and actually prevent diseases, because you predict these happenings before they actually occur in the person's in the biological system in the person's body. So I think that that's very fascinating, and that there needs to be more development there. And then
Okay, on the pathology side and clinical side, good.
yeah, and some hardware applications too. I think hardware and software is something I'm also very interested in right now. Space.
Good.
Yeah.
Anyone else? Okay, Sahel says, I'm interested in deep learning and generative models. Good. Maybe Aditya or KVBRR, Kubber. Okay, otherwise I'll just dive right into it. So I want to talk about AI and ML for science. I picked 4 areas. First, I wanted to give a overview, not only recent history, also some of the deeper history, the last 100 years, and look at how the interaction has happened historically and how that's really changed, and setting up how that's changed recently. And maybe in ways that are different from a popular narrative, what people are used to hearing in headlines. And then we'll be in a good state to look at applications for the common good. Some recent areas for human health and environmental good. And I have some sort of a quiz to see if you can guess what entity is the landing page. I screenshotted the web page and hid where it was coming from, and see if you can guess.
Mm-hmm.
And then we'll be set up to look at state-of-the-art tools, some tools that I'll focus more on some of the molecular biopharmaceutical areas, so some of those tools. And then at the end, educational advice. So my dream degree, because everyone is good at turning other people into themselves. So if I don't know if my advice is good exactly for all the areas you're in. If you're in aerospace, what do I know about aerospace? If you're in chemistry, it's a bit closer, but I wouldn't call myself a chemist. If you're in structural biology, yeah, then I think it would be the closest fit, and my dream degree. Okay, so let's just jump right into it. This is the famous Flammarion wood engraving. This was done in 1988. It was a accompanying illustration to actually a textbook on or monograph on the atmosphere and popular meteorology. And you can see here in this stylized colored version, we have the phenomenological world with the sun and human artifacts of buildings and sculpted landscape and trees and stars and the moon. And then we have this meeting of the sky and the land, and peering beyond, underneath the curtain of phenomenal nature, into this world of the wheel within the wheel, the hidden order and patterns and logos that everything, cause and effect, relationships. And I would take this, the reason why I chose this to put in to start with, is that you have modeling on one side and data. So we have our data, what we interact with, the kind of raw stuff in the phenomenological world. And then we have our imaginative mental models of how it plays out. And that's so much a part of science. Science gives a very rich tradition of things that seem to work, things that are interpretable, things that are maybe convenient to work with mathematically. The next idea I want to share is the principle of least action. So this is an optimization principle. Here we have Euler and Leibniz. The principle of least action was an optimization principle. It was a search for something that, from that principle, the equations, the laws of nature would follow. One principle. And it can actually, you can look it up on Wikipedia and see the equations, what action is and what it means to have the least amount of it, you minimize this integral. And it's used to derive Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics, even general relativity with some modified action. The physicist Richard Feynman applied it in principle to quantum electrodynamics. And so this is happening in the 1700s. Leibniz is sort of a bit before then. And the flavor of physics coming out of these approaches is very analytical. You have symbols that allow you to peer into the future in an instant. You can just have a closed form evaluation and presto, you get your answer, predicting into the future. And I would contrast this with a computational approach. Here we see the great-great-great-great-grandmother and grandfather of hardware and software, Charles Babbage and Ada Lovelace. And they're working on their analytical engine in the 1830s and 40s, and there's great resources to learn more about this out there. This is from a kind of graphical novel. And it's a different style of doing science, computation. And they were sort of before their time, and did the analytical engine ever really get fully built and used to its potential? You can read the history books about that. There's other pioneers like Claude Shannon. We recently celebrated the centenary of his birth. Father of information theory, very influential in electrical engineering, coding, signal processing. Here's a picture of Sewall Wright and a causal diagram where you have relationships and this graph and information propagating. This was formalized by the great, I'll just skip that slide here, great computer scientist Judea Pearl, to engage more seriously with causality, not just seeing data and finding associations. Well, what if I see someone who's has scurvy? What if I see someone, what is causing that scurvy? What if I see that they're having this type of kind of citrus intake? Oh, that means that that means that there's an association, there's a correlation between the citrus intake and interventions. Okay, well, let's have really good boiled concentrated citrus juice and intervene and have sailors have it when they're on long voyages. How would I intervene? How would I do something? How would I cause something? That actually happened in historically. Sailors started boiling citrus water to have more concentrated anti-scorbuents, and they were killing and breaking down all the vitamin C, and so it didn't work. You had citrus fruits, but they had to be fresh. And counterfactual reasoning, imagining possible worlds. What if I didn't do this, what would happen? And Judea Pearl developed a calculus, a notation, a computational process of notationally holding on and representing these ideas, these abstractions. So you could go beyond just having Bayesian conditioning to having notation to intervene, and this causes that, and this is part of this control group, and if I didn't do this, what would happen? And concluding, making causal conclusions from observational data under certain conditions. I would say the invention of the first digital electronic computer in the Institute for Advanced Study, where all these authors were in the 40s and 50s, unfortunately working on applications for weapons that would destroy so many lives. That was the money they were getting. They were getting the bomb money. And there was a big divide between the cultures of pure and applied mathematics and science, chalk versus code. And I don't think we've yet recovered from that. There's still too much an artificial division between the whiteboard and your IDE. This is wonderfully written about in this long historical account by the technology historian George Dyson, son of Freeman Dyson, who was at the Institute for Advanced Study. And look out for Christopher Nolan's upcoming film on Robert Oppenheimer. And then we can look to someone like Stephen Wolfram. Maybe you've used Wolfram Alpha for help with your integrals. Oh, all those trigonometric substitutions under the square root so difficult, and cosecant, and let's just double check in Wolfram Alpha to make sure I got the right answer. And it's all those complex numbers. Oh, I have to say that it's real, and not show that I is the not an imaginary number, it's just an index or something. And his, although I don't know that much about it, my sense is that there's a big cultural difference that maybe is keeping people far away from his work and a bit suspicious of his work, because you actually have to go through the process of simulating, of doing the computations, of running through the computational graph, of doing the game of life in order to get an answer. You can't jump ahead. You can't go to the end and have your final solution and an explicit equation that you've solved your differential equation from with your 10 pages of doing derivatives and integrals and sums and taking limits. You have to go through the process of computation. And sometimes what you're simulating is like, as it can start to get closer and closer to the complexity of what was actually happening in nature. And here we have in 2018, the Turing Award for Deep Learning. And so here you have a older Yann LeCun, Geoffrey Hinton, Yoshua Bengio, and younger versions where they're actually doing the work. There's a riveting account of the past 10 years from, let's say, 2010 to 2020 from Kate Mess's group, popular account, historical genius makers. He goes into what's driving these people, what's inside of them. And I would say there's another opportunity to have a cultural divide, or to have something that's more integrated, drawing on all the sources of intelligence, more Renaissance. There's an opportunity now to not kind of split too artificially science from computer science, science from engineering, modeling and parametric forms and inductive bias from data-driven machine learning approaches, black box approaches. Just like there was an opportunity that, Institute for Advanced Physics, Institute for Advanced Study, it lost its opportunity to keep developing this first digital electronic computer. They said, well, actually, we're more of a pure research area. And some companies are going to work on that, and that's it. And they closed up shop. And all the engineers went and worked other places, and IBM developed this one, and that company developed that one. And things happened at the national labs to really push performance. And there's a fork in the road these days. Okay, so that's maybe a generic sort of history. And now I'm going to talk a little bit more about my area of expertise, which has to do with small molecule drugs and folded proteins. Chemoinformatics is like a Frankenstein version of machine learning that chemists invented. Early history of chemistry, you have all these chemical abstracts, you have piles and piles of books. How do we represent with the notation, with the language? How could we search? How could you people used to go through and flip through and look up their chemical and find tabulated information about it through all these pages. And now this is automated. You can just quickly type in you can draw your molecule, you can have some canonical formula for it, and you can search that, and it outputs, okay, this is the molecule you need. Think about doing that with a word, right? We have an alphabet, we have simple rules of in English, right, with the Latin alphabet and maybe some punctuation and spacing. But chemicals, they're not even in 2D, they're in 3D. They have connections or they don't have connections. They have symmetries or broken symmetries of enantiomers and mirror images. Here we see a really early introduction of the idea of a graph from a chemical graph from chemistry, but the different ways things can be connected by this analytic geometer back in 1867. So chemistry has a long history, right? And chemistry is really the most data-intensive area of science. Maybe because it's simple and there's only so many atoms and they can only connect in certain amounts of ways, and especially in kind of the terrestrial conditions that most of the data is collected at and relevant for. We've developed a universal language to describe compounds and chemical structures. We've made progress in automating querying computer databases to this has been really important for patent offices in the past. That's what was driving it. We can convert chemical structures to strings. And so there was, chemistry's own version of ML. And maybe around 2015, David Duvenant at U of T and Gilmer at Google were maybe trying to generalize some of the choices that had been made to do something a bit more abstract and using approaches from deep learning to represent the properties of molecules. And there's been an explosion of work in the past 8 years in this area with making big impacts. So there's a poster from the team at Novartis at a major computer science conference I attended in the fall in December in New Orleans. And they got, something together in under a year, I believe, and accepted and published in that conference. There's also, modern software tools to be doing science in, that it becomes more easier to describe the language of science. Of course, there's a long tradition of writing scientific simulators, going from parameters of how something is oriented and its energy level and maybe the types of atoms and how much they interact with the type of probe that's imaging them, and then writing a program, writing a digital twin of your photon, electron, neutron probe and spectroscopy and microscopy, and then having some output. What if you want to go the other way? Well, statistics is a long tradition of solving inverse problems, going from data to model. And what if your probabilities here, your likelihoods, your priors, aren't just tight closed form solutions where the math is elegant and works out a la the pure science at the Institute for Advanced Study, the chalkboards filled with equations, the rotated pages so you can write your long equations by 11 and 8.5 instead of 8.5 by 11. What if your model is some physical simulator with if and else statements and all sorts of branching and new variables introduced if you take if the logical flow follows down a certain path, how do you invert that? And that's the area of probabilistic programming, where computer scientists sort of generalize statistics computationally. Maybe you can think about it like that. Generalized Bayesian inference computation, or attempted to in certain circumstances. So what's the connection of that and deep learning? Well, you can add in probabilistic structure into deep neural networks. You can have priors over the weights. You can have distribution, you can have parameters that go to distributions, parameters of distributions that are then sampled from. Maybe some people have seen variational autoencoders, for instance. So then you have this marrying of probabilistic programming with deep learning, and you have deep probabilistic programming languages. There's some intersection where you have some things that are just PPL languages and some things that are in neural networks, part of a larger class of the chain rule, automating the chain rule. And there's an intersection of differentiable probabilistic programming inference approaches, like variational autoencoders and Hamiltonian Monte Carlo. There's others. There's a long history of probabilistic programming languages from the 90s in stats communities or machine learning communities or AI communities, programming language communities. And it sort of ends around in the 2010s here. But here's this is from a recent summer school that I attended in last summer in 2022. And we were discussing some of the probabilistic programming languages at the very end as cutting edge examples where you try to close the loop. You have something that's end to end. You have your hypotheses. You have something in the physical world. You have approaches that are analyzing it, that are marrying different analytic approaches and data-driven, approximate functions and fitting them that are sort of learning to store, learning new equations from the data, learning new aspects of relationships from the data that maybe our modeling traditions left out or that we don't know how to model. Making conclusions, observing, generating the other question, thinking about it, thinking causally, thinking observationally, counterfactually. There's more and more science tracks at computer science conferences. There's at NeurIPS this year, there was AI for science. There was machine learning for structural biology. And that concludes my overview of the history of AI and science. So maybe I'll pause here and answer any questions about that area before moving on to some applications. Okay, I'll continue on. So that's nice. And what are we going to do with, you know, all that amazing research that has been publicly funded, all that hard work of other people? How are we going to save our planet and not destroy it, not destroy each other? Okay, quiz. Whose landing page is this? Who says we work on some of the most complex and interesting challenges in AI?
DeepMind.
Yes, DeepMind, yes. Very good. Okay, so if you click on the Sciences tab, although they have neuroscience, but there's so much, it's just a separate group. They've separated neuroscience from science. We can see some examples like with restoring and attributing ancient texts. Maybe even. So if you click on the science tab. Yeah, go ahead. Okay, you muted yourself. Or with physics. This has to do with fusion, magnetic control of tokamak plasmas through deep reinforcement learning. So learning how these plasmas are so hot and they can't touch the walls of this chamber, but are controlled with magnetic fields in order, you know, to not get out of control, and how they're able to monitor them in this kind of chaotic, turbulent relationships, and change what's happening with the magnetic fields around them with electrical currents so they can control this. That came out a year or two ago. This was really interesting. Advancing mathematics by guiding human intuition with AI. So AI has AI assistant to a mathematician. Okay, whose landing page is this? I'll read the quote here. Over the coming decade, deep learning looks set to have a transformational impact on the natural sciences. The consequences are potentially far-reaching and could dramatically improve our ability to model and predict natural phenomena over widely varying scales of space and time. Our AI for Science team, question of who? AI for Science of what team? Encompasses world experts in machine learning, quantum physics, computational chemistry, molecular biology, fluid dynamics, software engineering, and other disciplines, who are working together to tackle some of the most pressing challenges in this field. So who's Frank Noe and Max Welling? Who are they working for? Who do you think? AI for Science, yes, but what is AI for Science under? Yes, Microsoft, exactly, Microsoft. And so Microsoft is active in this space. Here we see, and what are some of the breakthroughs, more breakthroughs, right? So 2 years ago, the breakthrough of the year was protein structure prediction. This was out of DeepMind. They did a head taller in restricted, controlled community challenge from a sequence predicting one static structure. So these are data where the structure has been determined with a structural biology technique. They hold out that data, and then they just give the sequence, and you have to predict close. Okay, I have a question here. How do you think AI will evolve in the future, especially considering our newfound appreciation of its power, concerns about its safety? Yes, okay, well, we'll see. We'll see if we can get to that. Good question. I think it's very much in our hands. I do think it will start to have impacts on science and creating new materials, designing new materials. Okay, so what are some of the tools? So first we have tools of data. Here's a bioinformatics shared service that many of the kind of back-end infrastructure of public bioinformatic resources use, and that some small, medium enterprises also use in domains like chemical biology and enzymes and evolution and phylogeny, right? Evolutionary history, and scientific literature, molecular and cellular structures, proteins, proteomes, different types of cloud computing and software tools to have kind of easy workflows and not reinventing the wheel and wrangling the data again and again, and kind of solving that and having some standards out there, an API. Now, this is part of the EBI, the European Bioinformatics Institute, kind of a hub with Elixir sharing the same space. And maybe you've heard of UniProt and SwissProt and PFAM and gene ontology and scope and cath and protein structure. These are the ways, the models, the ways we're imagining things, the ways that different types of measurement techniques that measure magnetic field perturbations or diffraction patterns from X-ray crystallography, magnified images from electron microscopy. Then they reconstruct into a common space, a language that we understand, our mental models. And you could always go deeper. You could, not have a point to describe where an atom is. It could be, where the nucleus would be, but you don't have enough data and information to infer that. So you only represent it up to a certain level. For chemoinformatics approaches, okay, I showed a lot of pretty pictures. Now, maybe for some boring, more meatier ones, some nuts and bolts. This is a great open source library, RDKit, for doing chemoinformatics. This is, it's a fairly permissive license, and it's got Python wrapper. It's really a one-man shop who's built an amazing community around him, and who's now, his post is senior scientist at ETH Zurich. But I think this is like his life's work here. It's got very fast things for molecular operations and fingerprinting and all sort of the language of describing and encoding chemical knowledge. So you can get some data from some of those resources, analyze it and parse it with RDKit, and then have it going into deep learning tools that are generic and probabilistic programming languages. Here we see some modern PPLs. I've used and enjoyed Pyro. It's written on top of PyTorch. You have your model and how you do inference. So you can fully specify the model. You can have learnable models where you're fitting parameters, and you can have, repeat. You have lots of data and repeat and not just make conclusions for that specific data point, but more or less for data that looks like that, and learn relationships that will scale to using on new data. Or you can do, if you have very few data points, you want to learn as much as possible with those data points. You can have other approaches that really dial down on specific measurements. Here's just some screenshots of a generic PyTorch workflow where, yeah, you would have some approaches that RDKit or some other things, BioPython, that get things into tensors, and they have your PyTorch model or TensorFlow model or JAX model, and then after that, you're looking at the documentation, generic documentation that's out there, learning communities. And this is a real benefit and power of deep learning, that there's large communities out there, and also ML communities like in scikit-learn, large communities out there that you can benefit from and learn from and debug, and you're not sort of getting stuck, and really tried and true APIs. Different examples from other areas. Maybe there'll be more and more examples from science, niche areas of science. And if you're in your senior undergrad or in grad school, you just dive in the tutorials. You just figure it out. You just jump right in, and there's all sorts of online courses and videos up, and learn through doing. And it's the same whether you settle on TensorFlow. What I found is that there's maybe more academic projects that use PyTorch, so more code freely available. I don't really know why. It's all very much the same. TensorFlow has a kind of more adaptable nuts and bolts aspect to it, and then it has a higher level of abstraction for beginners where you can, or just for prototyping, you quickly do something in Keras, but it's very much connected between TensorFlow and Keras. And also JAX, I really highly recommend if you like NumPy and Python, you look into JAX, which is close to the math. You have operations very close to the math. You're taking grad, Jacobians. It's a compiled, it compiles, so it will allocate memory before, so it becomes efficient. So that's a lot of work that they do in order to, but at the same time, maybe there can be, I would be using it if it had better sparse array support, but it just doesn't for whatever reason. Maybe that's harder to do. You have to allocate all this memory beforehand. You don't know exactly where it's going to be because things are sparse. Okay, so, and there's also Julia. So Julia is a wonderful language that's very popular, and I would say the hard science community, physics community, geosciences and other areas of physics, maybe not so much structural biology, life science community, but there's less tools out there. There's less of a mature ecosystem. You have to do things more your own and write things your own, but there's definitely a lot of learning resources, and it's marketed as a kind of all the benefits from performance from a language like C and C++, but at the same time benefits from being able to rapidly develop and write and execute of an interpreted language. I'd also say that when you writing, I've used like Julia for some courses in optimization, and when you write algorithms, the Julia code looks very close to like a pseudocode algorithm. It's close to the math, very much so. You can even have Greek letters and do some typesetting within your Julia code. Okay, so what about, so that's great, all those tools there, but maybe now you have the opportunity to set yourself up and aim for that space, aim for that area. There's some time, you're in your second year, your third year. What does a natural science core curriculum look like at many research universities, at least in the ones I know in Canada, US, North America, probably many European universities? Well, you have, natural science. So I don't know, the sciences that are heavy on the math. So not biochemistry, probably molecular biology, anatomy, physiology, not things like that, which tend to be not heavy on the math. Maybe biochemistry is a bit arguable there, but I would say it's not. And you have some mathematics, maybe you're doing physics, maybe you're doing chemistry, maybe you're doing chemical physics or physical chemistry or whatever sort of combination of words people do to market the new things. You have math, calculus, you have linear algebra, differential equations, geometry, proofs. You have some probability and statistics. You have computing courses. Maybe they're called scientific computing, high performance computing, or you do projects where you just use some language and you can learn how to numerical recipes, the modern day numerical recipes. Maybe you take some physics courses, the 101, and then some deeper ideas of thermodynamics and mechanics and E&M, stat mech, optics, relativity, particle physics, biophysics, physics of life, environmental physics, or chemistry, all these different areas of chemistry. How much computation is in these areas, is in this tradition? When we have computational chemistry here, maybe there's some simulations in stat mech that are sort of connected with probability. And with signal processing, yeah, there'll be some fast Fourier transforms. Those are good to do on the computer. There'll be data visualizations. But if you're in data science, right, you're going to get algorithms. This is taken from the DSCI at UBC. It seems like new and good. I suspect it's not too new and it's running smoothly. These titles seem good to me. You have algorithms and visualization, some data wrangling, some software engineering, development, workflows, applied ML, deep learning, and AI. Maybe that's different from computer science, where you have more math, algorithms and more algorithms, discrete math, optimization that's emphasizing the interplay between math and how it plays out numerically, more numerical linear algebra, and then programming languages, parallelism, specific areas of ML and AI. So my dream degree has more math than computer science does. It has more computation and programming languages than natural sciences do. It has more implementation and workflows, kind of like data science has, than computer science. My dream degree has lots of optimization and numerical linear algebra and deep learning. It has more advanced math. There's quite a bit of math. I don't have a background in computer science. My background's elsewhere. And when I came into computer science, I was quite surprised by how little math, how shaky a lot of people were in math. I thought everyone would be math was, and then I looked at the undergraduate degree. Well, it makes sense, right? But there's a lot of really interesting math that connects with, it's very computational and it can be applied in science, measure theory, differential geometry. There's lots of math on YouTube. I would definitely take real analysis, absolutely, and some harmonic analysis and the kind of underpinnings of Fourier transforms, which can then be extended to things that are more exotic geometries. There's really good advanced computer science courses and statistics courses with Bayesian inference and graph signal processing. and not to be neglected is YouTube. There's a lot of really good YouTube playlists. I put some in the kind of basically coming up and finishing now, where you have Crash Course, you have 3 Blue, 1 Brown. There's a lot of good stuff out there. So here are some books to read and educational resources to go into, and maybe, deep learning is certainly a fast area, but maybe applications into science might be a little less fast moving, because it takes time for scientific theories to people to do experiments, communities to get used to thinking about things in a certain way.
Mhm.
This is a great book about information. It's a good kind of history of computer science. I think it's still an open question about what is the future of computer science as a discipline. This hardware software dichotomy, along with that kind of last. And the last link here is to Udaya Pearl's Book of Why and causal inference. That still hasn't made that much impact on molecular sciences, where there are a lot of data collected with high throughput measurement instruments. But I think it's coming. Okay, thank you very much for your attention.
This was extremely, extremely loaded. I have a question here.
Yes, I'm listening.
Okay, yeah. I'm actually my name was Charles Sarton, but that's not actually my name. I had to rechange it so you don't miss it. So yeah, so I'm Ivan Sarton, the guy who was doing biomedical engineering and computer science. That's gonna be my start. Now I had a quick question. First of all, you mentioned that your dream courses or whatever is a certain one. Can you go back to that slide?
Yeah. Let's go
Yeah.
back. This one?
Yes. So what's the impetus behind this dream course of it being all of these? Like, obviously you've taken many of these.
To be a glue person, a back-end researcher at AI for Science or Deep Learning Science Initiative, to be a glue person that can be interfacing between science and people that will come from pure computer science backgrounds that would maybe know more about the bleeding areas of compiler optimization and database performance. And
Okay, and why is that though? Like, what's the impetus? Is it that there's much innovation that's going to happen there that you're like, oh, goodness, I'm so curious, or is it just I just wanted to understand like the impetus behind, like, because I'm also very much interested in like AI and biology. Like,
I think it's my dream because it connects so much of what I've learned. Yeah, and that's very fulfilling and satisfying. It unites, intelligence and that creativity aspect with an engineering component where you actually bring it into reality and create something and end up, solving that disease, curing that disease, or having better treatments, matching people with good treatments.
okay. Could you give like a use case of like, maybe the technology is not out there yet, but an example of what a use case of this study, or like possible solutions?
Well, all the ones I showed. I think all the things that AI for Science and deep learning, Deep Minds science projects, something like AlphaFold, absolutely. So
Okay,
you look
those
at
are the-
AlphaFold, you had to have ideas from ecovariant neural nets, geometric considerations about how to connect these sort of triangles of they had a representation and of kind of pairwise distance constraints, and then trying to connect that back to what's happening in 3D.
Okay.
There's
So
a lot
like
of numerical linear algebra considerations in how backpropagation itself works.
yeah. Okay.
And
So
then if you scale things up to be, very, very large, there are, numerical representations that can exploit sparsity and that can have good preconditioners. You have to, people that it's those ideas and nuts and bolts. Those errors exist because people do hit snags and they hit walls, and they need to, there's developed bodies of work out there solving that because people encounter those issues and they're taught in advanced courses.
Okay.
And I've had to go there and take that stuff in order to know why something's not working, why my out of the box, approach is not really working that well.
So with taking having a degree studying biomedical engineering and computer science relate with this more, or is this computer engineering that relates with this more, or is it systems engineering? Because all three are sort of parallel in some way, but which one is most?
I would say if there's some things happening with robotics, some of the numerical linear algebra and differential geometry and harmonic analysis, and I could see graph signal processing and contact optimization, probably. I could say many of these things. Okay. What is biomedical engineering?
Am I understanding?
Yeah, or what area of biomedical engineering are you specifically aiming towards?
Well, based on my current
data, is it image data? Is it sort of
based on my current knowledge base right now, using MRIs, right now is really expensive, but how can it be scaled in a much smaller scale such that they can be used for personal use rather than just really expensive?
Yeah, and so that's a great example of fMRI, and there was some really interesting approaches in compressed sensing that is drawing on some ideas from the foundations of probability and random matrix theory and optimization, numerical and linear algebra, and then to actually implement it would be numerical aspects, where you would have to collect less data. You can have quicker scans. This is for clinical MRI, and it's mature enough that there's in my home province, in the capital in Victoria, there was a partnership between a research hospital and a company to buy their new machine, and it's supported by the kind of cutting edge algorithms and white papers on that and webinars. And I emailed the kind of person who was a clinician and researcher who was quoted in the newspaper, and he pointed me to the company website. And if you want to work for a company like that, developing a product like that, or work be in a research group that's interfacing with a company that's developing a product like that, it's going to be built out of it's going to come down to math and statistics and computation.
Okay, so you just mentioned career stuff. So what companies? Because they did mention in this was, you would mention educational paths, startup paths, which you just mentioned right now.
Yes.
So in terms of career first, let's say you're interning at a biotech company, etc. Which ones are you are?
Well, it depend on the biotech company. So, do you have some concrete group in mind, and what types of data they're using, and the scope of the project?
Well, again, with my current knowledge base, I'll say DeepMind is one.
Okay, well, I talked a bit with there's a new spin out from kind of the AlphaFold people from Alphabet called Isomorphic Labs. So they have offices. So it's not DeepMind, but it's people maybe that used to work for DeepMind and that are now going to work for this new company, Isomorphic Labs. They have offices in London and Lausanne in Switzerland, I believe. And they're a drug development company. And so they'll have, people that are deep learning experts, software engineering experts. They'll have people that are, computational chemists. Computational chemists would definitely know a lot of numerical linear algebra, optimization. He would have some sense to talk with the deep learning people, how to kind of make this work. And there'd be a lot of, and then there's a lot of domain experts involved, where you also have to have a lot of familiarity with what types of data, how much noise there is in them, how cheap the data is to collect, how long it takes, how wide the scope is. And maybe that's what some of the, typical natural science core curriculum can give you, right? But I felt very much that the natural science core curriculum that I received was like only teaching me math from 80 years ago. And that so much had happened in operations research, with resource allocation in World War II, with using computers to, numerically optimize things in an iterative way and direct solvers, that it was like so much had happened and I was left out of the party. And those were the tools being used in papers in the journals I was following. And this is some of the area, right, kind of on the, that I think has a lot of juice to squeeze into science, or that has yet to be squeezed by many people because it's not as common. You have to make a harder effort.
Okay. All right.
And it's an effort that companies are really looking to do and to maintain a competitive edge. So maybe you can't learn all of these areas, but you can find know some aspects of convex optimization or differential geometry, and then connect them to a science problem and a type of data, and that's your tool in your toolkit. That's what kind of you can bring to the table that other people wouldn't have, instead of just having generic approaches. Oh, I can solve this Kaggle data science contest with this typical tabular data using all the tools everyone else uses. And
okay, and in that, now I have a little bit more philosophical questions, because I are not too much philosophical, but before that, what projects would you recommend? Like, okay, one should be building or can build in this pathway.
well, for like fMRI stuff, for your
no, like beyond that scope, like this, what you just mentioned here, like there isn't much innovation or much things happening in this space.
I think there's good stuff happening at the Broad Institute. So this is in Boston, and it's affiliated with MIT and Harvard and the Broad. This is like high throughput molecular life science data, a lot of DNA, nucleic acid, RNA-seq type of data. Then there's really cool stuff happening in structural biology, protein structure biology, whether it's with X-ray crystallography or cryo-electron microscopy and other scattering techniques.
So what projects would you recommend building with this knowledge set?
Do you want something a bit more concrete than what I mentioned?
Yeah, like an end case. For instance, one of the projects that actually the hackathon project, a few hours with this group, is to be able to bring the data sets from the data sets in terms of detecting disease like retinal disease or from through diabetes. So basically there's a data set that's already out there because they've already done the model, right? And then be able to bring that data sets such that users can input images of the retina, and through this model that's already is existing, we feed that data into the model and the output comes out whether they have through their eye retina whether they have diabetes or not, based on this already existing model which researchers have already built. So that's one of the project examples that I'm thinking of other projects as well. So what could you recommend in that regard?
Well, you could start with having enough data available. That's not too much of a pain to wrangle. So you could decide on your form of your data, whether or not you want to have small molecule data or larger biological molecules, or something that's more integrated with connections between treatments and diseases and other electronic health record information.
Mhm.
I think that, once you commit to that, then it becomes more clear. I'm really excited about a lot of electron microscopy data because it's image-based, yet it's molecular. So you have scientific knowledge about how to represent things in parametric forms. You have traditions of how the imaging devices work. You have forward models where you can simulate the measuring devices, the forward model, the digital twin of the microscope, and then come up with different approaches to invert it. I think for a hackathon project, it's it can be good to use it as an opportunity to get your feet wet with a tool you want more experience in. You don't want it too complicated, too hard to do, and then it just doesn't really come together. Maybe let's pick something not too complicated, interesting idea, but keep it a little bit more minimal viable product prototype, and do something with JAX. And depends what your motivations are for a hackathon, right? Do you want to learn from other people? Do you want to have something for your portfolio? Do you want to have something you can continue to, you want to sort of jumpstart something and then continue to work on it after?
Yeah.
But you definitely don't want to pick the most great idea to change the world, to solve everything, and then you oh, how do I open this file? Oh, this is too big. I can't download this. I don't know what this means. I don't have and then installing stuff, and then you just run out of time and pick the most generic thing, black box thing that's out of the box, and then predict a very simple thing about it, and it's what's the point of that?
Yeah. So that was my initial thing, thinking about the MVP product first, minimal viable product, before anything else. So you mentioned the 3 threads, so the product, and then so what products are you suggesting to build for the hackathon? Because I already have one, but does it maybe other threads?
Yeah, I don't really have any to suggest. Should ask someone else.
Okay, sure. All right. Now to my philosophical questions.
Oh, those are the ones I like.
Oh, interesting.
And the historical ones.
Sure. So what is critical thinking, and how can you develop critical thinking for scientific discovery?
I think it's really important to have also a liberal art education, to think critically, to be a free thinker, to study logic and rhetoric. Some of my favorite authors are Mortimer Adler. He wrote a book called How to Speak and How to Listen. We have lots of practice writing and getting evaluated on writing, all this time reading. But unlike other countries, there's more an oral culture. We don't really get evaluated on how we speak. And do we even get advice on how we listen? Do we even know how to be a good listener? And that's what he set out to do in that book. And I'm a big fan of his work. And maybe there'll be a resurgence of oral examinations with remote learning and remote exams where it's impossible to prevent people from cheating. You have to do a live exam. You can't wiggle your way out of that one. I think philosophy is also, I would not contrast philosophy with science. I think they're very much on a spectrum of reflective thinking, foundational thinking. Some of my favorite philosophers, in fact, I think all of them started out as scientists. Aristotle, well, not all of them, but many of them. Aristotle, he was a biologist. People like Mariana Ortigas, Robert Koons. Yeah, they come from Tom McLeish, the poetry and music of science. He studied French literature as a minor when he's a polymer chemist, and he studied the minor French literature. He's in the UK, I think at Durham University right now. Also, like you have to be your own goalie coach. A goalie coach coaches the goalie on, they review tapes and videos and, oh, you should have put your blocker up here and you should have cut that in your net and your skate should be closer together. So with all these Zoom calls and YouTube videos, there's workshops that, you bring that after you've accumulated some material where you're talking out loud, and then you analyze it and go over it and say, oh man, I'm saying too much, or the way I end my sentences doesn't sound like I'm that confident. I have to finish and lower my voice and pause. Too many ideas. I'm all over the place. I just need 3 ideas. 1, 2, 3. I'm not an expert in that area, but I have read some things. And there's a good style guide called Style by the University of Chicago. It's like a modern day Shrunken White writing guide. There's a wonderful logic textbook and philosophy textbook by Peter Kraft, Logic, 3rd edition. It's very Aristotelian. My favorite philosophy area is philosophy of nature. How it all comes together, all these niche areas, evolutionary biology, structural biology, ecology, how it all connects to our vision of like how nature works, what we're surrounded with, what we're part of, what we're inside of. And then I think that gives a lot of motivation to go deeper in science. It's not just about curiosity and about competitiveness. We are really listening to the kind of message and how things actually work and adapting to it, and listening and figuring out the kind of grammar of nature.
Geoffrey,
Yes.
it would be really great if you could answer. There were 2 questions from the stream
Okay.
a bit earlier.
So we had
I
from
think
704, you posted me. How do you think AI will evolve in the future, especially considering our newfound appreciation for its power, about its safety? I think ever since we dropped this atom bomb, horrendous mistake to drop this atom bomb in Japan, and even before that, maybe with all these chemical weapons in World War One, we really, in Western context, have been unsure of our power. Do we have power over our power? And a big question I'm wary of and vigilant for is our agency, human agency. Algorithmic ethics, when it's so easy for things to be automated and decisions to be made, are we passing the buck? Are we passing the potato? There's been some studies where, let's say people are rolling out some police surveillance thing or recidivism, right? If this criminal should be convicted criminal and he served a sentence, should be released early or not. Or just job evaluations for a teacher. Should they continue to be a good teacher? Let's say you have your office acquires some AI assistant. Nope, you should fire the teacher. And maybe it's good, maybe it's not good. Maybe it's fair, maybe it's not fair. Let's say you say, well, okay, it says fire the teacher. Well, you can say, well, it's just the thing that told me to do it. I'm just doing my job. It said fire. Let's say it said fire and you said, no. I say, don't fire. He's had human evaluations that are good. And then something drastic happens. Something bad happens. Well, you might get in trouble. And so you sort of take responsibility onto your own hands when you go against a recommendation system. And so people tend to defer to something, to transfer responsibility. And in many mission critical areas, I think we have to be very vigilant of it. Okay, another question was, looking to explore AI a bit using Python, no prior experience, would you recommend using PyTorch or TensorFlow or something else? I would recommend using PyTorch and JAX.
Awesome. Thank you, Geoffrey. I think that those were all the questions from the different places. All right. Thank you so much, Geoffrey, once again for doing our talk here today. And thank you to everyone who showed up. And I will be ending the YouTube live stream.
I had a great time. I hope everyone has a great family day weekend.